Hello, this is Dr. James Holt with Engineering and Technology Management's program at Washington State University. Tonight I have a little tidbit here for you called the sixes game. You know, we waste a lot of time in our projects, and I think maybe you say, what do you mean we waste time? Perhaps I can show you what I mean here with this little game called the sixes game. Projects, you know, are things which seem to take too long. They're usually late, they're over budget. Why is that? Well, we've got a lot of excuses, you know. I didn't have enough safety, there wasn't enough time. After all, I couldn't finish everything you wanted me to do, and there wasn't enough money, blah, 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 blah. How long have people been trying to fix these kind of problems? Years and years and years. Can there be a simple solution? Wouldn't that be nice? Well, let's play a game. In the sixes game, we take a fair die. I have one here. You can tell that the fair die is fair because on opposite sides they add to 7. This one has 5 on that side and 2 on this side. This one has 4 on that side and 3 on that side. This one has 6 on this side and 1 on that side. If it's other than that, it may not be a fair die. But anyway, we take a fair die, and my question is, how long is it going to take me to roll a 6? Should I get it in the first roll? Should it be 6 rolls? Could it be more than 6 rolls? Let's see. Okay, well here's my die. Let me roll it and see, and I'll count how many times it takes to get a 6. It's a fair one. It's got a 6 on there, so let's not it's not biased. 1, 2, 3. Okay, that's pretty easy. Let's do it again. 1, 2, 3. Whoops, didn't get it in 3. We got it in 3 last time. 4, 5, 6. I should have had it 7, 8, 9, 10, 11, 12. There's a 6 on there. 13, 14. Whoa, 15. I hate this one this time. It's 16. Okay. Whoa, that took forever. 16 rolls for that thing? Man, 15, 16, that was, let's see. You know, I did this once with a group of about 20 people, and that's how many it took. I was lucky. Some of those guys were way over 20 rolls to get a 6. Why is that possible? How is it possible? What does this distribution look like? Well, it should be obvious that if you have enough people rolling, there's going to be somebody who gets a long number, because this is a negative exponential distribution. The probability of getting a 6 on the first roll is 1/6. The probability of getting a roll on the second roll is 1/6 times 5/6 raised to the 1. And to get it on the third roll is 1/6 times 5/6 raised to the 2. It's a negative exponential distribution. Looks sort of like that. And just because I've stopped at 29 on this graph does not mean that it doesn't go farther. Chances are slim that it'll happen, but it can happen. Interesting. That's a world problem we got there. Now, here's the cumulative probability. If I add the probabilities up, it starts off here and says, how long does it take? When I get up there about 29 days, it's almost 100% sure you're going to be less than 29 days. Now, if that's the accumulation for the curve, and it says here that about 90% of the time it'll be 20 or less, and about 50% of the time it'll be 9 or less. Now you understand the curve. Let's suppose that you're a contractor, and your business operates like this die, meaning you roll this die, and that's going to tell us how long it's going to take you to finish your project. The number of rolls it takes to get a 6 will determine how long it takes you to get the project. And here's the deal. I will pay you 100% of the contract price if you roll a 6 within the time that you tell me. But if you are late, then I'm only going to pay you 50% on the project. And by the way, I'll never contract with you again. So, I'm going to ask you now. Contractor, how many rolls of the dice are you going to take you to get this thing done? What's your bid on the contract? How long's it going to take you? How many times are you going to have to roll? What do you think your guess is? Is it going to be 9? 50-50 chance of completing on time? Probably not. Is it going to be 15, somewhere around 80%? Is it going to be 20 at 90%? Is it going to be 45 to make sure, absolute sure you'll make the contract on time? Well, I tell you, if you're over 20, I'm not going to contract with you because I got to get this project done, right? All right. Well, let's agree that we all understand that what you're doing and that you need to be safe, and so you contract for 20 days. Now, what does that mean to me? I'm the guy who wants the project done. Well, if I've got 10 guys, and each guy's a contractor, and they all want 20 days, the flow time from beginning to end is going to be like 200 days. So, I need to get 10 rolls of 6s. How many rolls is it going to take me to get 10 6s? Do you think I'm going to get it in 200 rolls? Well, yeah, I hope so. Don't you realize that every contractor is acting to protect his own self-interest? He wants to deliver to his promise to you. He wants to be ethical. Now, that can't be bad, is it? No, he's trying to deliver to his promise, but he's trying to protect himself as well. He wants a future contract with me. So, that's great. But don't you realize that we weren't talking about contracts? We were talking about the people in your organization. Because every person who is in your organization wants to be ethical too. And these people who do projects in your organization are going to do the same thing as a contractor. They want to deliver to their internal promises. Their promises are just like internal contractors to you. They work there to try, and you pay them, and they work there because they want to be there. If they didn't, they'd work somewhere else, right? Just like a contractor would. So there's a couple of interesting things about DICE and beta distributions and projects. The beta curve is widely accepted by academics to describe the individual task in a project. We use this curve to try and say how long it will take to complete a particular task. We see it has a skewed distribution, primarily because if it takes an average of 5 days, but there's no way you can do it in negative 5 days, but there's highly likely that it can take 10, 20, or even 30 days, it has a skewed distribution with a long tail off to the right. I was studying a different problem for a student one time, and I came across this situation where they had a situation where there was a process where the first task had a 70% rework. And then once it got through, if it made it through there and it finished, then there was a 40% chance it would go through the line quickly, the following tasks. But if it went through, there was a 60% line they would have to go through a long road to get through the end. And so student asked, and I knew there was a way to calculate it mathematically, but couldn't find it. And so I said, well, I'll just whip it into my simulation program. So I simulated it 5,000 times, and I came up with this particular curve, which looked just like the beta distribution as how long it would take to get from start to finish on average based upon a 5,000 time sample. This gave me a real shock because when I calculated the probability density function of getting a 6, that is, you take the number of rolls it took and multiply it times the value, like 1/6 times 1, and then 1/6 times 5/6 times 2, and then 1/6 times 5/6 times 5/6 times 3, and so on, and all the way up to 20 and so on. The probability density function looks like this, which is almost identical to the beta distribution where it goes from 0 to 50 with the alpha of 2 and a beta of 8. So what an interesting problem this was to me when I realized that the 6 is really a beta distribution all on its own. So if we take the probability, cumulative probability of rolling a 6, there's a 50-50 chance that it's going to be less than 10 rolls. If it's less than 10 rolls, then the contractor who was telling me he needed 20 rolls was ripping me off at about half the time. Because on average, 50% of the time he should have made it in 10 or less. So what if I tell a contractor, look, you just do the best you can, get it done as fast as you can, and then just tell us when you're complete. And what we'll do is we'll put everybody together and then we'll take some of the safety we took away from you, we'll put it at the end of the project. You don't have to meet your 10 days, just do it as soon as you can and tell us when you're complete. What we get is a changed system. Before we had 10 contractors, 20 rolls each. Afterwards, we get 20 contractors, 10 rolls each. So instead of taking 200 days, the aggressive target now is only 100. This schedule is much, much better, but what's the probability of completing 10 tasks, each one with a 50-50 chance of success? Pretty slim, so that's not going to work. But if we take back half of the safety that we took out, that's 50 days we can add on the end. So now we can put that in there as a safety and protect not the individual contractors, but the system as a whole. What we find is we can complete in 150 rolls 95% of the time. Look at this one on the beginning. If you have 10 contractors and each one's going to take 20 rolls, what's the probability that one of those 10 is going to go more than 20 rolls? We're going to be late. If we take the one that says 50-50 chance of getting a 10, but we roll them and the average is 10 or less, most likely we're going to be able to easily complete in 150 days. This buffer really adds a lot of space and gives us lots of capacity, a lot of safety, a lot of predictability, and we can be on time. This is a really good condition, and if we're a little bit late on this short one, we're not late by 50 days, and so we're going to be really great. A great way to make some money. So I encourage you to try it. You'll like it.